Hello everyone, this is Dr. A classes for BTech students. This lesson introduces the fundamental topic of petrology, a cornerstone of engineering geology. It explores the study of rocks, their origin, classification, formation processes, and characteristics that influence their engineering behavior. It is designed to equip BTech civil engineering students with essential geological understanding needed for evaluating construction materials, site conditions, and the long-term performance of civil engineering structures. Learning objectives of the courses, understanding the fundamentals and scope of petrology to recognize its importance in studying earth materials for engineering applications, learning the classification of rocks, igneous, sedimentary and metamorphic to identify the most suitable material for construction projects, recognize rock formation processes and texture to evaluate performance under different environmental and load conditions, evaluating geological materials to make informed decisions on material selection, foundation design, and ensuring structural integrity, assessing key engineering properties of rocks to support the design and safety of critical infrastructure such as dams, roads, tunnels, and buildings, exploring the rock cycle to predict long-term geological changes that may impact construction sites and the stability of materials over time. What is petrology? Petrology is derived from the Greek word petra meaning rock and logos meaning study. So it is the study of rock. It is a branch of geology that focuses on the composition, structure, origin, occurrence, alteration, and classification of rocks. Petrology aims to understand the processes responsible for the formation and transformation of rock over time. It links microscopic mineral features to large-scale geological processes, providing insights into Earth's dynamic system. What is a rock? Rock is a naturally occurring solid mass composed of one or more minerals. It forms the foundation of Earth's crust and is found everywhere from towering mountain ranges to the ocean floor. Rocks vary widely in appearance and texture. Some are hard and compact like granite, while others are soft and crumbly like shale. These differences arise from how the rocks were formed over geological time through processes such as cooling of magma, compression of sediments, or transformation under pressure and heat. From an engineering point of view, the term rock is more specific. Engineers define rock as strong, solid material capable of supporting loads. This contrasts with soil, which includes loose particles, unconsolidated sediments, or heavily weathered rock fragments that lack cohesive strength. It is also important to note that rocks are not always completely solid. They often contain tiny pores and large fractures. These spaces may be filled with fluid like water, air, or other substances. The presence of such fluids can greatly affect a rock's strength, stability, and behavior, especially in construction or foundation work. Importance of studying petrology. Studying petrology is essential for understanding the origin, composition, and transformation of rocks. Rocks are natural records of Earth's geological history, capturing events like volcanic eruptions, tectonic shifts, and climate change over millions of years. They are essential for locating valuable resources such as minerals, oil, gas, and groundwater. In construction, rocks influence foundation stability, site selection, and material choice. Rocks also contribute to soil formation and affect water quality through weathering and mineral content. Studying rocks on other planets helps us understand the composition and evolution of celestial bodies. Thus, rocks are vital in geology, engineering, environment, and planetary sciences. Classification of rock. Rocks are broadly classified into three main types: igneous, sedimentary, and metamorphic, based on how they form. Each type has distinct characteristics and origins, playing a unique role in Earth's geological structure. Igneous rocks. These rocks form when molten magma or lava cools and solidifies. If the cooling occurs beneath the Earth's surface, the rock is called intrusive igneous rock. If it happens on the surface after volcanic eruption, it is called extrusive igneous rocks. Examples are granite and basalt. Sedimentary rock. These rocks are formed from the accumulation of sediments like sand, silt, and clay. Over time, these sediments are compacted and cemented together, often in layers. Sedimentary rocks frequently contain fossils and are usually found in riverbeds, lakes, and oceans. Examples of sedimentary rocks are sandstone, limestone, etc. Metamorphic rocks. These rocks originate from existing rocks, igneous, sedimentary, or even older metamorphic, that undergo transformation due to intense heat, pressure, or chemical activity without melting. This process alters their structure, texture, and mineral composition. Examples of metamorphic rocks are marble and schist. Understanding these rock types is essential for identifying Earth's material, studying its history, and applying geological knowledge in fields like civil engineering, mining, and environmental sciences. Rock cycle. The rock cycle is a continuous natural process through which rock changes from one type to another over geological time. It explains how the three major types, igneous, sedimentary, or metamorphic, are interconnected through Earth's dynamic system. The cycle begins deep within Earth, where rocks melt into magma. When this magma cools and solidifies, either beneath the surface or after volcanic eruption, it forms igneous rock like granite or basalt. Over time, igneous rocks are exposed to the surface, where they break down through weathering by wind, water, and temperature changes and erosion. This process produces small particles or sediments. These sediments are transported, deposited in layers, compacted, and cemented together to form sedimentary rocks such as sandstone, limestone, etc. When these sedimentary rocks or the igneous rocks are subjected to high heat, pressure, or chemical changes without melting, they transform into metamorphic rocks. Examples include marble from limestone and schist from shale. If the metamorphic or any other rock type is pushed deeper into the earth, it may melt into magma, restarting the cycle. Distinguishing characteristics of rock. The table provides a concise overview of the fundamental differences between the three major rock types, igneous, sedimentary, and metamorphic. It outlines key characteristics that geologists and engineers use to identify and classify in the field and laboratory. These distinguishing features include the origin and formation process of each rock type, the resulting texture and structure observed in hand samples or outcrop, the typical layering patterns, the presence or absence of fossils, the general mineral content, and whether the rock exhibit a noticeable reaction with acid. By comparing these attributes, one can systematically differentiate between rocks that have solidified from molten material, accumulated from deposited sediments, or have been transformed by intense heat and pressure. This comparative framework is essential for understanding Earth's geological history and for various practical applications in construction, resource exploration, and environmental management. Assessment of rock properties. Accurate assessment of rock properties is fundamental to making safe and informed engineering decisions during project planning and execution. Let us briefly look at why this is critical. Essential for safe and successful project planning. Knowing the rock type and behavior helps prevent design errors and site failures. It ensures the chosen approach is suitable for ground conditions. Influence design, schedule, cost, and feasibility. Rock properties determines the construction method, time, and cost. Misjudging them can lead to delays, added expenses, or design changes. Critical in civil, mining, petroleum, and energy sectors. From tunnels to dams and oil wells, rock properties impact safety, efficiency, and performance across multiple engineering fields. Directly impact constructability and safety. Weak or fractured rock can pose safety risks during excavation or drilling. A strong, consistent rock supports stable construction. Understanding variability in structure is key. Rock is naturally variable. Recognizing changes in structure or strength across a site is vital for reliable design and construction. Identifiable rock properties. Rocks can be identified based on certain properties which help classify them into igneous, sedimentary, and metamorphic type. Their ability to resist weathering and their density also play a key role in determining their formation and durability. The properties are color, appearance or shade of a rock based on minerals it contains, grain size, the average size of mineral particles or crystal in a rock, texture, overall appearance of the rock surface based on size, shape and arrangement of grain or crystal, fabric. Fabric refers to the orientation and spatial distribution of minerals or structural features within a rock. Structure, large scale features of rock often visible in field, minor lithological characteristics, secondary features, that assist in rock classification and interpretation. Strength of rock material, the resistance of rock material to failure under applied stress. Color. It is the visual appearance or shade of a rock surface, primarily influenced by its mineral composition and weathering state. Rock-rich in felsic mineral like quartz and feldspar tend to be light-colored, white, pink, or gray. Rock with mafic minerals such as pyroxene, olivine, or amphibole are typically dark-colored, black, green, or gray, or dark gray. Oxidation of iron-bearing minerals can impart a reddish or yellowish hue. Example laterite. Color provides clues about the rock mineralogy, degree of weathering, and potential durability. Grain size. Grain size refers to the dimension of individual mineral grains or particles in a rock. Coarse-grained rocks, example granite, have visible grains formed due to slow cooling of magma leading to stronger interlocking grains. Fine-grained rocks, example basalt, form from rapid cooling resulting in tiny, tightly packed grains. Clastic sedimentary rocks like sandstone may have varying grain sizes based on depositional energy. Grain size affects porosity, permeability, and strength. Coarse-grained rocks are often stronger and less porous. Texture. Texture describes the physical characteristics of a rock surface. So it is overall appearance of rock surface based on size, shape, and arrangement of grains or crystal. Types of textures are crystalline texture. Grains are interlocking and often visible. Gabbro-granite examples. Clastic texture composed of fragments, particles cemented together, shales, conglomerates, etc. Glassy texture is smooth and non-crystalline, often from rapid cooling of lava, example obsidian. Porphyritic texture, large crystals embedded in a finer matrix indicating two-stage cooling. Texture influences mechanical properties like strength, weathering resistance, and suitability for construction. Fabric. It refers to the orientation and spatial distribution of minerals or structural features within a rock. Foliated fabric shows planar alignment of minerals often found in metamorphic rocks, example slate sheets, etc., formed due to directed pressure. Non-foliated fabric has no preferred orientation, quartzite, marble, etc. Lineation is a linear fabric formed by stretching or deformation. Fabric affects anisotropy in strength and deformation, which is critical in tunneling, slope design, and excavation planning. Structure. Structure includes large-scale features seen in rocks or rock masses that reflect geological processes during or after rock formation. Common structures are bedding and lamination, horizontal layering in sedimentary rock, joints, natural fracture with no significant movement, often affecting rock stability, faults, fracture along the displacement has occurred, potentially weak zones, faults, bends in rock layers due to compressive stress. Structural features dictate rock mass behavior and influence stability of slopes, tunnels, and foundation. Minor lithological characteristics. These are secondary features or inclusion in a rock that may not dominate its composition but provide significant information about its history and environment. Fossils in sedimentary rocks reveal depositional condition and age. The veins, quartz or calcite indicate past hydrothermal activity. Concretion and nodules suggest chemical sedimentation. Weathering pattern or discoloration may reflect chemical alteration. These features can affect rock integrity, permeability, and suitability for a specific engineering application. A strength of rock material. It refers to the ability of a rock to withstand applied stresses without breaking or deforming. It is a fundamental property in engineering, geology, and geotechnical design as it directly influences the performance of rock in construction and excavation. Several factors influence the strength of rock material, including its mineral composition, the degree of grain interlocking or bonding, and the extent of weathering or alteration it has undergone. Rocks with strong mineral bonds and minimal weathering typically exhibit high strength, while weathered or fractured rocks are significantly weaker.
Rock strength classification. Rocks are typically classified according to their uniaxial compressive strength, which is measured in megapascal or MPa. Based on uniaxial compressive strength values, rocks are grouped into strength classes such as very weak, having the value of less than 1 MPa, easily broken by hand or light, common in highly weathered or soft rocks like chalk or claystone. Weak, having the value of 1 to 5 MPa, can be broken with some effort using a hammer, often includes siltstone and some shales. Moderately strong 5 to 25 MPa requires considerable force to break, includes fine-grained sandstone and weathered granite. Strong 25 to 50 megapascal. Hard to break manually includes most intact limestone and some igneous rocks. Very strong 50 to 100 MPa. Extremely difficult to break includes dense igneous and metamorphic rocks like basalt and gneiss. Extremely strong more than 100 MPa. Practically unbreakable by hand tools including unweathered quartzite and granite. Rock strength classification is crucial not only for material selection but also for designing support system, evaluating excavation techniques, and predicting ground behavior under load. By understanding the strength classes, engineers can make informed decisions about construction method, safety factors, and long-term stability. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully, answer these questions based on understanding of the topic, review any concept you are unsure about. The questions are: what is the rock cycle? Briefly explain its significance in earth processes. List and describe the three main types of rock based on their origin. Give two examples of each. Explain the difference between intrusive and extrusive igneous rocks. Provide one example of each. Why is rock classification important in civil engineering practices? Give at least two applications. Explain how weathering affects the strength classification of a rock. Why is it necessary to classify rock strength in civil engineering projects? Discuss.
Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thanks.